Hey guys, today we're going to go over a couple examples of combining equations in a way that the College Board and AP likes us to be able to do. Before we can do that, I want to talk briefly about centripetal force to clear up a common confusion that some students have. And then, like I say, we'll go through a couple examples of combining equations. Now, this particular video is mostly for the opt-out students. I've gone through this material and these examples live with the students that are able to attend in class. So those of you who have been in class and seen this, this is just a repeat of what we talked about in class. So it's here for your, excuse me, for your review if you need it, but there's nothing new here beyond what we did. So first, centripetal force. There's a common misconception among students. Centripetal force is not a type of force. Okay, centripetal force simply talks about the direction of the force. So as you recall, if something is moving in a circle, it has a centripetal acceleration, which is an acceleration toward the middle of the circle. And to cause an acceleration, you need a force, and that force is centripetal force, as the equation mv squared over r, which may ring a bell, maybe not. But again, centripetal force is about the direction of the force acting toward the center of the circle. It is not a type of force. And what do I mean by that? Types of force are like gravity, or normal force, or friction, or tension, magnetic force, electrical forces, static electrical forces, etc. These are the types of forces. And if one of these types of forces is causing something to travel in a circle, then it happens to be a centripetal force because the direction of the force is toward the center of the circle. So for example, the moon. We know if the moon goes in roughly a circle around the Earth. And since it's going in a circle, there must be some centripetal force forcing it to go in that circle. And in the case of the moon, the type of force is gravity. That's what keeps it in orbit. So gravity acts as a centripetal force directed toward the center of that orbit. Gravity is the type, centripetal is the direction. Likewise, if you have a roller coaster that goes through a vertical loop along the track, it's going in a circle for a while, so there must be some centripetal force acting to make it go in a circle. And in this case, it's the normal force of the tires on the track or the wheels on the track. If the train was just sitting in the station, not moving, there's normal force from the track pushing up on the wheels of the train, keeping it from falling into the basement. That's a normal force holding the train up. And when you build the track into a loop, then that normal force is always acting toward the center of that circle. So normal force is the type of force, but it is directed to the center of that loop. So let's go to our document camera here. All right, so there's an experiment that is done in physics quite a bit. I'm not a huge fan of it, so I don't normally do it, especially if something has to cut out, like for COVID or something. But the idea is you have usually a glass tube or like a very robust plastic straw with a string going through it. And on one end of the string, we usually use a rubber stopper, like you put in the top of a test tube. That's tied to one end of the string. And then the other end of the string has a weight hanging off it out of the bottom. And you hold on to this this straw like this, and you twirl it around and around in a circle so that the stopper goes in a circle around, a horizontal circle around and around. Okay, now since the stopper is traveling in a circle, we know there must be some centripetal force acting on it. And in this case, the centripetal force comes from the tension in the string. The string is always pulling it toward the center, so it goes around and around. Now, why is there tension in the string? Well, there's tension in the string because we have a weight hanging off the bottom of it. So this weight is providing the tension, which in turn provides the centripetal force to keep this thing in a circle. Now, if we were to spin this thing too fast, then there would not be enough tension to keep it in a circle, and it would start to spiral outward and lift this weight upward. Now, likewise, if we didn't spin it fast enough, then there's more weight, more tension pulling in than is required to keep it in a circle. In that case, the stopper will start to spiral inward and get closer and closer to the center. So there's one ideal speed where we can spin this thing around at just the right speed, where the centripetal force required to keep it in that circle is equal to the weight of the mass down here on the bottom. So the experiment is to find the speed where everything balances and the weight does not rise and the weight does not fall, where everything is stable. Okay? So the question in this case is, what is the speed? We're going to find V, which is the speed of the stopper as it goes around. That's what we want to find here. Okay? And to do this, we're going to be combining equations. That's why this is an example. So we already know that there's centripetal force here, and the centripetal force, try to remember what that equation is. What is the equation is for centripetal force? Pause it if you need a minute to think about it. But the centripetal force is mv squared over r. So that's one expression that helps us describe this. Now, the thing that is providing the centripetal force in this case is the weight of this mass down here on the end. So the weight is F sub g, that's the weight, is mg, okay? And we know that these two are equal to each other when the system is stable. So that means we can combine these two equations. We can say mv squared over r is equal to mg. Now, there's a little problem because we have m in two different places in here, and we need to get clear in our minds what they actually represent. Okay, so up here for the centripetal force, this mass, what does this mass represent? Okay, and the answer is it's the stopper. So we're going to call this object number 1. We're going to call this M1. So M1. And down here, the weight of this thing, the M is the mass of the thing. So we're going to call this object 2, and this is object 2. So these two M's are not the same thing. They refer to different masses in the system. Okay, so we want to solve this thing for V, so we're going to rearrange our equation here, and we get V squared is equal to M2GR over M1. So we brought the R up to the numerator, we took M1 down to the denominator, and we get V squared. So if we want V, we got to take the square root of all of that. And we actually do have enough to feed all this now. So we wind up with M2, that's 50 grams, or 0.05 kilograms, because we really have to keep things in kilograms to make all this work, times 9.8 meters per second squared. That's why we have to go to kilograms and meters, so that it's all the same. R is the radius of the rotation, which is 0.2 meters. We're going to divide all that by the mass of the stopper, which is 0.025 kilograms, and we're going to take the square root of it. And this comes out to be, let's see, 0.05 times 9.8 times 0.2 equals, then we're going to divide that by 0.025 and take the square root, and we get 1.98 meters per second is the speed, the tangential speed of the stopper. Okay? So as I said, College Board and AP likes you to be able to do this kind of stuff. If they want you to be able to look at a system and find an equation which describes some part of the system, and then recognize that two things are equivalent and set them equal to each other. Then you isolate the variable that they're interested in. In this case, we wanted to find V, and solve for it and hang a number on it. And there you are. That's how we design an experiment. Now, the traditional way that this one works, this experiment works, is to find G, is to use this apparatus to determine G, which is 9.8 meters per second squared. But you want to see if you can do an experiment to confirm that. It turns out it's very difficult because it's difficult to keep this system stable as you're spinning it around and around. But it is kind of a classic physics experiment, and I think it's worthwhile for you to be familiar with.